All right, this is the remaining notes from section 8.6. We had a few examples that I said I would do on a video for you guys, so that's what this is going to be. The first one is, and this is mostly, for the most part, looking at the normal distribution or a binomial distribution, which is going to be then translated to a normal distribution. So if they already give you the mean and the standard deviation, and they usually will say like normally distributed in the problem, then you don't do anything weird. You just convert things to z-scores and you look up the percentages. But if you're dealing with, something where they've given you the probability of success and it's a fixed number of trials, you have a binomial distribution and you'll have to convert that to what we talked about in class, which is how do we estimate those rectangles correctly? And then, of course, we'll use our z-score chart. So this first one is a normal distributed one. So it's already a bell curve, essentially. So it says, on average, a student takes dictation at a speed of 100 words per minute. So that's our mean. And that's through an advanced court reporting course at the American Institute of Court Reporting, assuming that the dictation speeds of the students are normal and the standard deviation is 20. So we also need that. What is the probability that a student randomly selected from the course can take dictation at a speed of more than 120 words per minute? So the problem is you first have to get this into a z-score to be able to use it, because everything that is normal can be standardized. So remember, it's item minus the mean divided by the standard deviation. So this would be a z-score of 20 over 20, which is 1, and we're looking for more than. So we're looking for the probability of a z-score being greater than 1. Anytime it's greater than, you can either look up the negative or opposite sign and get the percentage right away, or you can do 1 minus the probability in the chart, which if you look up 1, it has a probability of, let's see, 0.8413, and 1 minus that would be hang on just a second, I wrote it backwards. Yeah, 0.1557. Okay, so someone being able to type more than 120 words per minute, there's only about 15.57% of the people in this course that could do that. All right, between means we're going to be going between two z-scores. Now we already know the z-score for 120 is 1. So we know probability that our z-score is in between 1 on the right side. We need to convert 80. So 80 minus 100 divided by 20, that's negative 20 over 20, which is negative 1. So we're doing, what's the probability that we are between negative 1 and 1? So we have to look up both of these, and then we're going to subtract the bigger probability minus the smaller probability. So if we look at the number 1, that is 0.8413 in the chart. And then negative 1 is the 0.1587. That's where I knew something looked funny. This was supposed to be an 8. I was trying to read it off my paper and it was really small, sorry. So that's 0.1587 for that guy as well, because that was the opposite of that. So when we subtract this, we're going to get, so I'm doing this on my calculator, 0.8413 minus 0.1587, it's 0.6826. Which actually makes a lot of sense. If you remember what we talked about in class, we said, because this essentially is going 1 standard deviation above and below, since it's exactly 1 and negative 1. If you look at that chart we had in our notes a few pages before this, it said that if you go one standard deviation on either side of your mean, that's 68% of the data. So this actually shows that that is true using our z-score chart. And then the last guy is less than 180. So we already know that 180 was a negative 1. So we're looking for the probability that the z-score is less than negative 1. Now that's directly reading out of the chart, which is 0.1587. Because anything in the chart is always less than. So there is example 1 from that section. Okay, example 2 is a little bit backwards. We're going to be given the percentages that they've split things up at, and we're going to try to work backwards and find the raw data score. So if you're starting with a percentile, you first have to figure out what z-score is going to be attached to that. So we're going to be reading the chart backwards, but we're going to have to estimate a little bit. And then we're also then going to have to convert that back into a raw data item, like a test score, because this is a test that has a mean of 70 and a standard deviation of 10. So our mean is 70, standard deviation is 10. Okay, so I'm going to draw a picture of this first because to see what they're doing, you kind of need to see the whole bell curve. They said the instructor is going to give A's to the top 15% because A is as high as you can go, so 0.15. And then they're going to give B's to 25%, so that's not quite up to 50% yet, so it's not half yet. And then they're going to give C's to about 40% of the class and D's to 15%. And then this last percent is going to get F's. So 0.05. So anybody in this category is going to get an F. So this line right here is what changes you to a D. This line is what changes you to a C. This line right here is going to change me to a B. And this line is going to change me to an A. So we don't really even care about the F's that are the bottom of the barrel. What we're trying to figure out is where are those cut scores where the letter grade will bump up one, because they only want the grades A through D. So we're going to draw a picture for each of these, starting with D. I'm going to be focused on that guy first because he's on the lower end. And remember, our chart always reads to the left, so that's going to help us. So imagine we don't care about anything else on the chart except that this guy is 0.05. So we want to know what z-score goes with that. So remember, you have to look into the chart where all the decimal numbers are. And this is obviously going to be a negative number. And if I look into my chart, which I can't project to you guys, but you have yours that I gave you, 0.0505 or 0.0495. Those are both really close. They're about the same away from being 0.05 perfectly. And one of those occurs at the z-score negative 1.64. The other one occurs at the z-score negative 1.65. So I usually split the difference when they're equally dispersed like that, and I'm going to say that this z-score is negative 1.645. So to go ahead and find the cut score, what actual grade did a student make to get a D? What we do is we use our formula for z-score, except we actually know the z-score. It's negative 1.645. We don't know what they scored on the test, so our item is going to be like X. We know the mean is 70, and we know the standard deviation is 10. So we're going to be solving this backwards. We're essentially given the z-score by using the percentile, and then we solve for the item. So we're going to multiply both sides by 10. That would make this negative 16.45. On this side, it would just give me X minus 70. And we're going to add over the 70 to this side. And when I did that, I got that the people who got a D in the class scored a 53.55, because this has obviously been adjusted. They had too low scores or too many low scores, and the professor is doing what's called adjusting the bell curve. They're giving people higher scores than they technically got by adjusting the whole class. So this is the cutoff to get a D. You had to score at least 53.55. So now we want to look at what do I have to do to get a C. So I'm going to do that one right here. Now, it's a little bit tricky once you move past the D, because what you have to realize is that the cut point is what we care about. C's cut point happened here in the second mark. We need to add all percentages below that to figure out where that is in our z-score chart. So this is 20%. So 20% of the class made either an F or a D, so we want to know what's that cut mark for a C. So if you look up 0.20, try to find the closest you can get to that in the chart. It looks like 0.2005 is the closest we can get, which is negative 0.84. So that's the z-score that this would occur at, or at least the closest. We're estimating, we know that. So then we set up our formula again. We say, okay, this is my z-score, and this is the item we're looking for, minus the mean divided by the standard deviation. So again, we're going to multiply both sides by 10. I'll do it in a different color this time. So that would be negative 8.4 equals X minus 70. Add 70 over, and that's 61.6. So this is the C cutoff. If you make a 61.6, you get a C. Okay, we have two more to do. We need to do the B and the A. So for the B, you have to add all the percentages that were below you. So that's the 20% we just did here plus 40 more. So that's going to be at 60%. So where is 0.60 in the chart? And that's going to be on the positive z-score side. So looking at my chart, let's see, the closest I get, it looks like 0.5987 is the closest we can get to being 60%, which is 0.25 as my z-score. And then we're going to do the same thing we just did. So we're going to do 0.25 equals x minus 70 over 10. Solve this one in maybe blue. So then we would get 2.5 if we multiply the 10 over x minus 70. So this means that people who got a B in the class scored a 72.5 as the lowest possibility. And then last one would be the A's. So to do the A cut score, we're going to, first of all, add all the percentages up to the A line. So that was 60% plus 25 more, so 85% in the chart. And when I looked that one up, I got that it was close to 1.04 because that guy comes out to, yeah, 85.08. That's the closest I saw. Everything else was a little bit too far away. So then we do our same thing again. 1.04 equals x minus 70 over 10. I'll solve this one in, let's say, purple. So this would be 10.4 equals x minus 70. So I would get 80.4 is the cut score for an A. Okay, so that's how you work backwards if they tell you the percentiles. You need to draw a picture of what it looks like, and then you find each z-score by building your way up from the left, figuring out what that percentile below it is, and then you solve for the item, plugging into your z-score formula for the z-score you know, the mean, and the standard deviation. So this one gives people trouble sometimes. I think there's only one of these in the WebAssign, and it only asks you for one letter grade. So if it just asks you for one of them, like I think it's something like A's need to be given to the top 15 or 12%, you just need to do 1 minus that percent to figure out what's to the left of it. So remember, if you knew that the top 15% were getting an A, you knew 85% were not getting an A. So, so if you're looking up the z-score, you do need the percentage to the left of your number. Okay, so we did talk about the approximation of a binomial distribution in class because we skipped those two so that we could spend time on this. I believe the only one we got to do though was example number 3. So I want to go through and do 4, 5, and I think I have 6 and 7 possibly. So let's look at, yeah, so we have 4, 5, 6, and 7 that we need to continue doing. All right, so number 4 says Colorado Mining and Mineral has 800 employees engaged in its mining operations. It has been estimated that the probability of a worker meeting with an accident during a 1-year period is 0.1. What is the probability that more than 70 workers will meet with an accident during the year 1 period? Okay, so first things first, we need to find, since this is a probability of success, even though that sounds horrible, getting in an accident doesn't sound successful, but we know the probability of getting in an accident is 0.1, so the probability of not getting in an accident would be 0.9. We also have a fixed number of employees. You don't use the more than 70 for your trials because when you see the words more than or less than, that's the part we're measuring. So the trials has to be the 800 people that they were talking about. So our mean is the number of trials times the probability of success, and we're counting accident as success. So 800 times 0.1 is 80. So they expect to see 80 people in a year get in an accident. The standard deviation, when you're doing a binomial distribution, is the square root of the number of trials times the probability of success times the probability of failure, which is always, remember, these are complements of each other. And when I worked that out, I got about 8.49. So remember, this formula is square root of n times p times q. Okay, the next thing we want to do is talk about what are we asking. We're wanting for more than 70 raw data items, which are people, to be in an accident. Now, remember, if you're looking at your item. we need to convert this into, what are we asking? So this is when we're in a binomial. That's what we were in originally. We want to know what's the approximation to do this if we were normal. And we talked about how binomial distributions, remember, we have those probability distributions, and when you put something down, you have a rectangle around it because it's a histogram. We're converting that to a nice curve. So what we need to know is if we're shading the 70 or not. Essentially, that's what we're asking. So more than 70 does not mean to include. So if you're not including the 70, because they did not say equal to 70, they said more than 70, and they didn't say at least 70, which also would include 70. That means we're not shading the bar 70. So what we learned is that's a half step difference. So this would go up to 70.5. So I'm going to be doing what is the deal if my y was 70.5. Now, once you figure out what your half step is, you're going to convert that to a z-score. So 70.5 minus the mean, which is 80, divided by the standard deviation, which is 8.49. So I need to get my calculator to do that. 70.5 minus 80 divided by 8.49. That's going to be negative 1.12 when I rounded it. So let me write that down. So this is negative 1.12. So we're going to put that back in as now I'm looking for the probability that my z is greater than negative 1.12. And since that's a z-score, we can use our chart. So we're going to go find negative 1.12 in the chart. And let's see where that is. Negative, let me double check my math too, because I typed that really quick. 70.5 minus 80 divided by the 8.49. Yes. So when I look up negative 1.12, I get 1314 as the decimal. But remember, this is a greater than, so we would be doing 1 minus 0.1314. Or you could look up positive 1.12. Remember, that's the opposite of that, and that should give you the answer is approximately 0.8686. Okay. So there's an 86.86% chance that a worker is going to get, or that more than 70 workers are going to get hurt. And that makes sense to me because they already expected 80. So we're saying even a lower amount or more. So this is the estimate for that. Okay, so let's do number 5, example 5, which is a quality control problem. It says Par Bearings is the principal supplier of ball bearings for the Sperry Gyroscope Company. It has been determined that 6% of the ball bearings shipped are rejected because they fail to meet the tolerance requirements. What is the probability that a shipment of 200 balls bearings contains more than 10 rejects? So again, the question is, are we including the 10 or not? But let's go ahead and get our mean. So our mean is that we have the number of trials is 200. That's how many balls are in the shipment. And there's a 6% chance that there is going to be a reject because we're saying reject is success here. So 200 times 0.06 actually comes out to a nice even number. It's 12. The standard deviation would be square root of 200 times 0.06 times 0.94, because remember you need the probability of failure, which is the opposite of that. So I get 200 times 0.06 times 0.94. That's 11.28, and then we want to take the square root of that. That is 3.36. That's our standard deviation. So remember, we're asking for more than 10 rejects. So the probability that an X is greater than 10, that means, remember, 10 is not included because they're saying more than 10. So we would want to bump that up to 10.5 when we do our conversion. So the probability that we're going from binomial to normal, and we're estimating that little rectangle difference. So we're going to say that y is greater than 10.5, and then we want to convert that to a z-score. So 10.5 minus 12 divided by 3.36 is going to be my z-score. So 10.5 minus 12 divided by 3.36 is negative 0.45. So I'm looking for the probability that my z-score is greater than negative 0.45. So remember, this is equal to the probability that z is less than a positive 0.45. So you can either do 1 minus and look up your current probability, or you can just look up the opposite guy sign-wise, and that gives you the complement. So 0.45 is 6736, so 0.6736. So there's a 67.36 chance that their shipment of 200 balls will contain more than 10 rejected ones for the ball bearings. All right, let's look at example 6. This one is one that I threw in here just to see if you're paying attention. Because a lot of times students will just get into one mode and then they don't really think about what was given in the problem. And I see students all the time trying to make a probability of success out of this type of problem after they've done a bunch of the binomial ones. This one does not need a binomial distribution. This is just normal, and it actually will say normally distributed if the probabilities work already in the bell curve. So all we need to know is that we already have our mean, we have our standard deviation, and we're measuring more than 35,000. So this would be z-score is item, which is 35,000, minus mean, which is 40,000, divided by standard deviation, which is 2,000. That's going to be negative 2.5. And we're looking for the probability that z is greater than negative 2.5. Okay, so when I looked that up in my chart, I got 0.9935 because I looked up the complement. I looked up what's below 2.5 instead of what's 1 minus what is the negative 2.5. Now there's a second question, so this is part A. The other question says, determine the probability that 4 tires selected at random will have the useful tread life after 35,000 miles of driving. So we're asking, what's the chances that 4 tires in a row would have this same amount of tread life? And it says assume they are independent. So because they're independent, that means the probability of tire 1 times the probability of tire 2 having it times the probability of tire 3 times the probability of tire 4. They all have the same probability since it's independent, and we know the probability of just one of them out of the group having this. So this is just 0.9935 times itself 4 times. So we're just raising it to the 4th power. And that comes out to 0.9754. So there's a 97.54% chance that 4 tires selected at random will still have that tread life. Okay, and then we're on our last one for the set of notes, and it is example 7. A marksman chance of hitting a target with each of his shots is 60%. Assume that the shots are independent of each other, so we know a probability of success. We know they're independent. He's firing 30 shots, so that's a fixed number of trials. So this is binomial. We want to know what's the probability he hits at least 20 times, fewer than 10 times, or between 15 and 20 inclusive. So the big idea here is going to be getting that correct half step, since this is binomial right now and we need it to be normal because this is a lot of calculations to do by hand. So our probability of success is 0.6, so the probability of failure would be 0.4. So remember, to find your mean, you need to do the number of trials, which is 30, times the probability of success. So 30 times 0.6 is 18. We expect him to hit 18 of the shots if he hits exactly his 60% mark. Standard deviation is going to be the square root of 300 times 0.6 times 0.4, which when I worked that out earlier, I got 2.68. So let's talk about A. At least 20 means greater than or equal to 20. So remember, if you think about where the rectangle 20 would be, if you were doing a histogram, we need to shade the rectangle. So if you're shading the rectangle and the label's in the middle, you're going to need to back down to 19.5 to include the whole rectangle. So this would be probability that y is greater than 19.5. So as a z-score, we have to do that. So 19.5 minus 18 divided by 2.68. I got that was 0.56. So we want a z-score greater than 0.56. So we can do 1 minus the probability of 0.56, which is 0.7123. And this subtracts to 0.2877. So for him to hit at least 20 times, that means 20 times or more, that's already way above his normal marksman. His normal marksman would be, if he randomly did this on one day, he would get 18 out of the 30 shots. So for him to do 20 or more and hit every one of those at that accuracy level that he's been using, it's going to be a lower probability. It's not impossible, it's just lower. Now, fewer than 10 times does not include the 10. So when we do our conversion, we have to be careful about that. So for part B, he wants to do fewer than 10, which means in terms of going to a normal distribution, we're not shading the 10. So we're shading below it, but not including it. So we're going to have to go down to 9.5. So our y needs to be less than 9.5. So my z-score for that would be 9.5 minus 18 divided by 2.68. That's the probability that his z-score is less than negative 3.17, which is very, very small. Remember, we usually say that most of the data is between negative 3 and 3. And if you look this up in your table, you'll see that it's almost an impossible chance with his level of accuracy in shooting that he would only hit 9 or less, essentially. And then the last one, part C, is between 15 and 20 inclusive. So I think you're kind of getting the gist of the half steps. I'm going to jump right in and I'm going to write this a little differently. So we want to do a little less than 15 since we're including 15. So that's going to be 14.5 minus the 18 over 2.68. That's one way to write your z-score. We can obviously work that out. And the other z-score is going to be a little bit bigger than 20 since we have to include that rectangle. So 20.5 minus 18 divided by 2.68. So that means our two z-scores are negative 1.31 and 0.93. So if I look up the first one, which is the bigger one, 0.93 is 8238, so 0.8238. Negative 1.31, I got 0.0951. If we subtract those, that gives us the approximate probability of 72.87% or 0.7287. Now, if they ask you to write it as a percentage instead of a probability, you do need to move that decimal 2 places to the right. If they just say, what's the probability, you can leave it as the decimal form. Okay, so that's the end of those notes. I will see you guys on Monday if you want to come to my office hours, or Tuesday for our first part of our final exam. So make sure you are studying those final reviews that are posted in IB Learn, and I printed out for everyone who is in class. I look forward to seeing you all this next week.